The modulo calculation is a mathematical operation which uses division with remainder. Though this may sound difficult, we already use it in our everyday life when talking about the time. Instead of talking about 14 a.m., we say 2 p.m., and instead of 18 a.m., we talk about 6 p.m. What we are doing here is subtracting 12 from any time past noon, meaning we subtract a full clock rotation of 12 hours. And this is already a calculation modulo 12, since we said that 14 is the same as 2 up to a multiple of 12. So, modulo 12 means that both terms are equal up to a multiple of 12. Mathematically speaking, we say that 14 equals 2 modulo 12. To better separate this from a common equality, we use an equal sign with 3 lines. Of course, we could have more than one clock rotation, or even a backwards rotation. Hence all of those numbers are equal modulo 12. In general, you can of course do this for arbitrary values other than 12. If you want, you could simply think of a clock with more or less than 12 hours. Let's have a look at the mathematical definition. Let a and b be two arbitrary integers which are not equal. Further, let m be a natural non-zero number, which is smaller than a and b. Then, a is equal to b modulo m, if and only if a can be written as the sum of b and a multiple of m. One says that a is equal to b modulo m. So, basically a and b are the same number up to a multiple of m. The following examples will illustrate the definition, and make you familiar with the calculation itself. First, we claim that 16 is equal 4 modulo 2. This is true. According to our definition, we have that 16 equals 4 plus 6 times 2. It is also true that 35 equals 2 modulo 3, since 35 can be written as 2 plus 11 times 3. Does 42 equal 11 modulo 5 also hold? No. Because there is no integer k such that 42 equals 11 plus a multiple of 5. But how do I calculate this? And in particular with larger numbers? Let's look again at example 2. We have to find out what 35 is equal to modulo 3. For this, we divide 35 by 3, which gives us 11 with a remainder of 2. Hence, we can write 35 as 11 times 3 with remainder 2, and therefore 35 equals 2 modulo 3. The division with remainder gives us our result as the remainder. Note that it is also correct to say that 35 equals 5 modulo 3. The division with remainder only gives the smallest positive integer value. Other solutions are also true since they only differ by a multiple. Consider the residue class ring ZMZ. This means we consider integers, but modulo m. ZMZ contains certain sets of elements, the so-called residue classes, which are written in square brackets. Only the residue classes from 0 to m-1 are contained, since 0 and m, as well as 1 and m plus 1 are each equal modulo m. For instance, the residue class of 1 modulo 5 contains also the -4, 6 and 11. Those values are all equal to 1 up to a multiple of 5. One says that 1, 6, and 11 are representatives of the residue class 1 modulo 5. This slide will demonstrate how to work with residue classes. We decide on modulo 5. First, we list integers, where we decide for simplicity on the numbers between -6 and 6. So far we have learned that two numbers are equal modulo 5, if they only differ by a multiple of 5. Therefore, we rearrange the numbers above. Starting with -6, we go 5 to the right to -1, and again 5 to the right gives 4. From -5, we move to 0 and 5 in steps of 5. The same process is applied to the remaining numbers. Those sets of numbers form our residue classes. We chose as a representative the smallest natural number, which is contained in this class. First, we get the residue class with representative 4, then 0 and so on. The residue class 4 also contains -6, -1 and 4. If we would choose different representatives, for instance 6 instead of 1, the residue classes are the same, since their representatives are the same modulo 5. In total, Z5Z consists of the residue classes from 0 to 4. If you want to learn more about interesting topics, visit embedded-academy.com.